Okay, thank you for the opportunity for me to introduce my work and my research at UCF. I'm Enxia Zhang, assistant professor at ECE. I have been very thankful for joining this big family. Since I joined, I get all the help with career life. Everything goes very well. So at UCF, I'm also start with doing radiation effects and reliability in microelectronics. And I have done all the research in reliability aspect. First, we do have done the radiation detection measurement, and that just summarize the basis of radiation interaction with materials. That's basic mechanism. Then we move on the radiation effect in the circuit level. Here, this is the examples for the circuit level, the board. This is the photonic circuit. The other is a big memory circuit fabricated by GlobalFoundries and collaborate with the GNC. So once we get the radiation effects and test the reliability, we move on to the red hard by either processing or by design. For example, just now, Cesar mentioned his circuit, his design architecture, and we can use that architecture to test the reliability in radiation the environment. And maybe you can get like optimize the design to secure the circuit board using under defense or space applications. So this is, I have been working with many agencies like Air Force Research Lab, Air Force Office for Science Research, Naval Research, NASA, Sandia, all those DoD-related departments. So I have been very thankful for their support. So I will be able to do all this research, and we can keep moving on this area at UCF for space application. So this the wide bandgap power devices. This is just one of the examples I have done in my career as far. For this, I have done 3D IC and 3D flash memory, and also the 2D material, all those radiation effects in this kind of advanced devices. Okay, now let's move on the wide bandgap power devices. Here it shows the wide bandgap. It plays major roles in the high efficiency power systems. So this is the major collaborations between my research group and between my research with NASA and Sandia for the power system collaborated for the lunar exploration. So wideband gap is like a big demand for the high efficiency power systems. So this talk main focus on the silicon carbide. That now that compare with the silicon carbide with the other band gap wide band materials. So this we can see the wide band gap compared with the classical silicon based devices. You have high breakdown voltage and low on resistance and high temperature, high thermal conductivity. Those are very good for space and power systems. Then from my research on the silicon carbide devices, we have done from the basis of MOSFET and studied the basic mechanisms on the first generation fabricated by Korea, then move on the vertical power devices with the super junction or with the charge balance devices from GE. So from all this temperature, we vary different temperatures, different get electric field, and we vary with the total ionizing dose and heavy ion for range of LET testing. So that can provide us feeling of how these devices are good for the space environmentals. This is the result for the bias dependence instability for power devices. As we know, this has been consistent issue from the first generation to the newest generation. We always see with the VTI shift because the temperature, because the interface traps density decrease with temperature, and the output count also varies with the temperature independence. So those are from all insistent for all the generations. And we are trying to think about ways to improve this instability before we put in the lunar project. Then for the TID effect in silicon carbide is because in the silicon carbide MOSFET, there will be dielectrics. So with the TID radiation, you can see the radiation can induce the VTI shift, and just because the hole trapping dominant in the device radiation response. And also the electric field in this will be a significant effect how those response in the radiation environment. So we need to think about the way how to improve dielectric quality, or with the different the bypass to mitigate the charge during the radiation to improve the radiation hardening. Then the other the key important one in space single event is the major issue and very disaster if there's anything happen with your application. So we did heavy ion testing at TEMU based on based on devices from GE. This is my student. He did this at the calculate data. I instructed for all the testing plan, the data analysis. We can see this will be the single event instruction is very significantly affected by the voltage ranging and LET, of course. And so we think about this, we can understand epitaxial level thickness and doping significantly affect the breakdown voltage. And also if we apply the field place, the structural changing will also significantly improve this lecture. So we did a simulation and also did a verification with different generations of the devices from G. This is going forward for optimization of the structure change. So this actually is a typical example for all the devices circuit in microelectronics. You can do the structural design to mitigate the charge, and by processing, you can also improve the reliability in all the devices. So from the fabrication from design to fabrication, every step matters. That's how we need to work together to get all the disciplines integrated. We can improve the space reliability in the space electronics. And then my research, not just research for my career, right? We need we need people to work, develop the strengths. So for my plan as a family here, so I still continue to do the radiation effects and reliability, including characterizing, analyzing, or promote the testing capabilities and the design capabilities, or the red product design. And we have clean room. We can use the modification of the fabrication process to improve radiation reliability in those parts. And the major part here is the workforce development. So this is the design we fabricate with our partners at the Skywater. And this is my high schoolers. I did training. I get high schoolers for summer intern every year, so they can get into electrical engineering or related the careers. Then this the graduate student who did the beam testing, and those are my students with at the conferences. So at here, I'm really planning to get all the workforce development here under with all the help from our department to get student training moving on. So I'm open for all the opportunity for collaboration, especially for workforce development and radiation effects for space application. And thank you for giving me the chance to present. I'm open up for questions.